All right, fantastic. Well, welcome back, everyone. I hope you enjoyed part one, and we are ready to go for part two. So we've heard about space collaborations. We've heard about the moon. We're going to go beyond the moon in our next panel. And so without further ado, I want to welcome our panelists who are already prepared. So thank you, panelists. And our fantastic moderator, Hiro Ono. So Hiro, it is over to you. Thank you.
Okay, welcome back and welcome to the second panel. This is the Beyond panel, right? The last panel was about the moon, which is very interesting, but of course that's not our final goal, right? That is where we begin. Because there are so many balls of rocks and ice floating around the space beyond the moon, right? So we're gonna talk about that. I am Hiro Ono. I am honored to moderate this panel with distinguished speakers. Since I am a roboticist, I brought a robotic assistant, Doraemon. If you're Japanese, you know him, right? Yeah, for those who don't know, he is a robot coming from the 22nd century. Right? He's a cat robot. Doesn't look like a cat. It's a long story, so just ask your We, like the last panel, we're going to start with the short presentations, but I would like to have plenty of time for discussions and questions. So, please keep 3 minutes. If you go terribly over time, Doraemon gonna kindly reminds you like. Okay. So this is actually the alarm clock I stole from my son. Okay, so let's go. First, a little bit about myself. As you can tell from my accent, I am a Japanese. I spent 22 years over there, 20 years here. If you care, I'm a Hanshin Tigers fan. Go Tigers, right? And Red Sox. Woohoo! My background is robotic autonomy. So, I spent a lot of time on the Perseverance rover. That's my mission. I developed the autonomous driving for that rover, which is going very well. I recently led the project to build a snake robot to explore Enceladus. All right, so let's hand it to Tomohiro Usui from JAXA.
3 minutes? Oh, okay. So this is a forward, right? Yes. Okay. Nice to meet you. And first of all, thank you very much for inviting me to that kind of wonderful workshop I'm going to enjoy after my talk. But okay. I am Tomo Usui. I am a scientist from JAXA. And, but I can define myself as a geologist. But I am not a bit of the unique because I can differentiate the other geologists from me is that I am a geologist not only for Earth, but also the Mars, Moon, and asteroid, geologist of the planetary bodies. And also I'm a bit of unique, not only to work for the other planet, and also I have worked the geology and the back and forth from the United States and Japan and the United States, Japan. When I got a PhD in Japan, but my study field is the California and the Colorado Plateau. And this is a picture back in like 2000-ish that I work for the study the Earth's water circulation using the rocks from the California. And I got a PhD in Japan, and after that, I moved to the United States. Thereby, I had a chance to get into the space program and also be a geologist of the more than the Earth's terrestrial, more than the Earth's, more than the planetary bodies. I was the member of the NASA's DOM missions, which is the NASA's asteroid mission, and also I was also thanks to NASA, I was a member of the NASA's Mars exploration rover Spirit and Opportunity. And this is the picture back in almost 15 years ago to see the launch of the Delta 5 rocket for the Dawn's launch. That was my memorial moment for me. And after that, almost 8 years ago, I joined JAXA, back to Japan, and I joined the JAXA because the JAXA started the Martian moon exploration missions. This is the JAXA's small body exploration strategy. We had the successful sample return mission Hayabusa 2010, and also like a Hayabusa 2 2020. And thanks to NASA, collaborating with NASA, we have a sample of the NASA's another asteroid sample return mission, OSIRIS-REx. And now we are ready for the next sample return mission, which is the yellow one, is MMX, Martian Moon Sample Return Mission. Mars has 2 moons, Phobos and Deimos. And then MMX will come bring the sample back from one of the Martian moon. I'll talk you later. So the JAXA small body exploration mission will go beyond the snow line in the future and outer solar system. And the others, we will step into the Mars program through MMX. And thanks to NASA, thanks to the United States, we have a strong collaboration between the Hayabusa 2 and OSIRIS-REx. We're gonna share the sample. And back in 2021, we share the sample, Hayabusa 2 sample from JAXA to NASA. 3 years later, last year, OSIRIS-REx sample, Bennu sample, asteroid Bennu sample from NASA to JAXA. So we're gonna exchange the sample. That is like, not only exchange the sample, to exchange the sample, we need to exchange the techniques, skills, and human resources between the two institutes. And also like,
Sorry.
1 minute.
Just a little bit.
So, future, 2031, 2020, we're gonna have a world first sample return mission from the Martian moon Phobos. Launch date is like next year, and also go to the Martian moon Phobos and Deimos, and get the sample greater than 10 grams from Phobos and back to the Earth, 2031. Stay tuned. And also we have a strong collaboration with the United States, because one of them is a gamma ray and a neutron spectrometer provided by the Johns Hopkins universities, and a pneumatic sampler from the Honeybee Robotics here, and also like testing activities in US facilities like Ames and Goddard, and also like a deep space network and navigation support mainly through the JPL. Thanks to them. And that's it. Yeah.
Okay, thank you very much. And the next panelist is Charles Wetzel from JPL.
Okay, I'm going to do my best to stay within my 3 minutes. Now that I know there's real consequences here. Hiro asked us to just prepare a couple of slides before we talk about some ideas, or actually what I want to talk about are some ideas and plant some seeds for potential future collaborations between NASA and JAXA. But I also wanted to share a little bit of our background, qualifications, sort of so you have a sense of the perspective from which we're talking. At JPL right now, my current role is the Moon to Mars Support Office, where I spent most of my career more as a Martian, but made a transplantation to the Moon about a year ago. And so we're looking for opportunities at JPL for us to apply what we've learned about planetary exploration in Mars to all of the initiatives and the new work that's going on the Moon in recent years as well. Before I took that position, I was actually in a position to oversee all of the engineering and science at JPL. So I got to see a lot of different activities going on there as well. Hiro asked us to share a little bit about sort of our personal life hobbies and things like that. For a lot of my recently, I have not had a lot of time for hobbies. We had my wife and I have 4 children. We've just become empty nesters now, so I'm starting to have a lot more free time to tinker and explore some things, makerspace. One thing that I've found really fascinating is I've had a little bit more free time and playing around with all the things now, machine vision, computer vision. It's just amazing how much that field has come and just what's available even in the open source libraries now. I'm able to get stuff that you can order off of Amazon or off of the internet and do things that 20 years ago, 15 years ago was state of the art, things that were being invented earlier in my career that's now just out there, and that technology base that we can build from as we move forward. It's just fascinating to think about that. Hiro also asked us to talk a little bit about our background with international partnerships again, so you get a sense of the perspective from which these are coming. I've not had the opportunity to work that closely with JAXA in the past, other than much earlier in my career, some review boards and some of our Earth science missions as well. But I've had a lot more experience on the Atlantic side of the partnerships than the Pacific side of the partnerships with our colleagues in Europe, both at the European Space Agency as well as the French Space Agency. Actually, Jason and I both worked together with the French Space Agency on an earlier incarnation of Mars sample return, and then have stayed engaged both with the French Space Agency and the European Space Agency on some of our Earth science missions, and fairly recently as the European Space Agency has gotten more involved with Mars exploration. So it's true we get so much more out of these when the partners come together and share across those boundaries. What I actually wanted to plant the seeds on or talk a little about the opportunities I'm excited about, building off of some of the comments from Amit Kshatriya earlier in the day in lunar exploration. And he hearkened back to his experience with the International Space Station and the partnerships and the science that was enabled through the NASA-JAXA partnership there. I'm extremely excited. I know this is supposed to be beyond the moon, but I'm going to take us back to the moon just briefly and share some thoughts on the lunar cruiser and what opportunities it presents there. That's not actually a picture. I had some fun playing around with AI-generated images for both of these. So that's an AI's concept of what a pressurized Japanese rover with a large robotic arm would look like on the surface of the moon. The International Space Station, as Amit emphasized, started out as how do we live in space, right? And I think it expanded so much beyond how we live and work and explore in space, right? And there are so many different science opportunities and science objectives that have been accomplished by the space station over the years that were never envisioned, when it was first on the drawing board or first getting started. And that includes not only biological sciences and the racks and the payloads that are inside, the pressurized volume inside the space station, but in these later years of things that have been mounted onto the outside of the space station for remote sensing, for Earth science, for all the different kind of science that has been enabled by having the facility and the infrastructure of the space station. And I think the pressurized rover, the lunar cruiser, is going to provide it's even some things that Hiro and I have already started collaborating on and brainstorming on about how to do more robotics, more science mounted to the pressurized rover. There's so many subsystems, power, communications, pointing that you can have for free because of the investment in the core vehicle itself. So that, I think, again, for both of our agencies, our countries to collaborate on, it's a really exciting time and a really exciting opportunity. Now, I will shift back to my home base in Mars and talk a little bit about collaboration that I think is going to be enabled in the 5 to 10 year horizon. NASA's Mars exploration program on the robotic side just completed a set of studies about commercialization of Mars exploration. And so it's kind of following the path down the CLIPS commercial lunar payload services. Our colleagues from iSpace talked about their experiences and what they're working on that front as well. I think, again, where that enables a core infrastructure, the idea with Mars exploration is that the agencies might buy a bus that would carry multiple small sets, multiple payloads, and again, amortize that cost over several different, smaller missions, CubeSats attached, detached, those sort of things. I think it's a really, as I was saying, it's a really exciting time where there are so many opportunities that are being enabled by commercial capabilities, new entrants into the space field, and it just really, what we're seeing in the CLIPS program, if that can be transplanted to Mars, where one vehicle is going out there and has the opportunity to fly multiple satellites, multiple science investigations, it really lowers that barrier to entry. I think you're going to see a lot of different other countries that are able to participate, and a lot of universities and smaller organizations that are able to participate as well. So hopefully we'll have a chance to come back to that during the panel discussion. But I just wanted to plant some seeds and share a few thoughts as kind of an idea guy about directions that we might go in future U.S. and Japan collaborations in the moon and beyond. So thanks.
Okay, thanks, Charles. Next, Stacy Weinstein-Weiss from JPL again.
All right, hi. For our guests, hajimemashite. Watashi wa Suteishi desu. I'm Stacy Weinstein-Weiss from JPL. I work in planetary formulation right now. I've had a number of roles over the many years I've been at JPL. The last one was Clipper Deputy Payload Manager for 5.5 years. And it's been a pleasure. During that time, I've been able to work on quite a few things, including something called MUSES-C, which we now know as Hayabusa. And that was way back in the early years before it was a launched project. But as Charles said, in addition to JAXA, we've worked with the European Space Agency in France, and the Italians and Germans, and it's been wonderful doing all that. In terms of personal, I'm the mother of a 10-year-old, and I don't have hobbies anymore because my hobby is driving her to her hobbies. But I used to have hobbies, and they were fun. Let's talk a little bit about MUSES-C. This was in the in the late 90s, and JPL and JAXA were trying to formulate a collaboration. And what we were working on at the time was bringing the samples back to the US. We're going to provide a landing site, deep space network time, a couple other things, and what's pictured up there is our nano rover. JAXA was going to drop off the nano rover on the surface of the asteroid and let it crawl around and do observations. And then in the end, we would get a portion of the asteroid sample back in the US as well. Of course, Japan would have the lion's share. Unfortunately, our nano rover was canceled. We went over budget. And the samples ended up being landed in Australia. But the rest of the collaboration held pretty closely. There was navigation support. We brought in airborne observations of the capsule reentry. And our scientists did get to collaborate on the sample analysis. Hayabusa was such a successful mission. I can't even believe how ambitious it was. And JAXA pulled off so many technologies that nobody had ever done before for the world's first asteroid sample return. It was a privilege to have a squishy, a small part in it. That's a picture of us back in April 1998, just for fun. It was shot on a film camera, if people know what those are anymore. That's why it's so grainy and poor. But notice it was April, it was cherry blossom season, squid on a stick. It was wonderful. It was delicious. What else do I have? I guess next, we'll just talk about going future. So, we've continued to talk, JPL and JAXA, NASA and JAXA, of course. Some of the things that we've been talking about in the last couple of years, outside of Moon and Mars, daughter craft. These are separable free flyers that could be used for many different things in planetary exploration, short-lived, or if a long-duration power source like an americium RTG were available, maybe a long-lived one. That could definitely enhance missions. And then also, there's a lot of interest at JAXA in atmospheric science, all aspects of atmospheric science, and of course, instruments to go along with those. We had some discussions on, conceptual Venus missions. NASA has gotten itself involved in a lot of Venus lately, and hopefully we will in the future. In terms of missions, just in general, there are kind of two flavors. There are the directed missions and the competed missions. The directed missions tend to be the big flagships, like Cassini or Mars Sample Return or upcoming, Uranus Orbiter and Probe, we hope. And then there are the competed missions, which are like New Frontiers or SMEX, the Small Explorers. For the directed missions, generally JAXA and NASA, have discussions and negotiations about, what part everybody gets. For the competed missions, it's a little bit more freeform, and the centers in the U.S. Have freedom within guidelines to go out and partner with individual international space agencies. So just so we know, the draft announcement of opportunity for the SMEX, the Small Explorer, is out, and we're hoping that we'll see one for New Frontiers in the next couple of months. So exciting times. And that's it.
Okay, thanks, Stacy. By the way, adding a little bit of context about why JAXA was looking for the landing site, there is no desert in Japan. Surprising for Americans, right? All right, so next one up, John Eiler from Caltech, please.
Greetings, everybody. So my name is John Eiler. I'm a geologist and geochemist working in Caltech's Division of Geological and Planetary Sciences. I've been here for about 30 years. And my reason for being here, my intersection with JAXA, is as an individual laboratory scientist collaborating with colleagues in Japan and in the US as part of the Hayabusa 2 mission. I thought the best way to explain myself to you is through a little micro science vignette, so you can get a feel as to what these sorts of projects are like and what these collaborations entail. So my story begins with the periodic table, which, depending upon how well educated you are, you saw first in grade school or middle school or high school, or maybe not at all, who's to say. But I then take a sharp turn from the periodic table you're used to and examine the naturally occurring isotopes like the common carbon-12, the rare carbon-13, the even rarer and radioactive carbon-14. My research group specializes in studying the uneven distributions of the rare naturally occurring isotopes across molecules, within molecules, atom by atom, various combinations. And this is it's a sufficiently complicated problem that we invent all sorts of technologies, advanced mass spectrometries, advanced methodologies for mapping out how nature has distributed isotopes at scales of individual molecules. This lets us do things like forensically fingerprint the origins of molecules. It lets us reconstruct environmental conditions, a concept we'll look at in just a moment, of the distribution of rare isotopes, like our little red spots in these molecules. They can be separate from each other, or they can gather together into the same molecule, and the difference between these states is a kind of thermometer. And then in addition, when we have data of this type for many molecules, we can reconstruct reaction networks like non-biological chemistry in the environment, or like your metabolism. All of these are open to study for us. So the problem that we worked on with the colleagues in Japan who led the Hayabusa 2 mission basically asked, why is the sky the color that it is if you had infrared viewing eyes? If you look up in space, the colors that you see in the infrared are mostly controlled by organic molecules. The chemistry of the universe is organic. And unfortunately, most of what you see is soot, okay, hydrocarbon materials. And this can be condensed from the envelopes of stars. It can be formed in disks where planets grow, or it can form in interstellar space, very cold. And one of the ways that we have examined this is we retrieved samples from Hayabusa 2, and how we got them is actually kind of the most interesting story. I'm not like an organization kind of guy. I like to just be in my lab and do my thing. But JAXA had an established collaboration with colleagues at the Goddard Space Flight Center, And they were working on the organic chemistry of the Hayabusa 2 samples, asking questions about the chemistry that enabled the emergence of life on the Earth and maybe elsewhere. And they had some difficulties with certain kinds of measurements, and they thought, maybe Eiler could do something with this. And so they just sent it to me. No paperwork, none of that nonsense. I have no idea whether I was supposed to have them or not, and nobody cares. I love that. That is exactly how this is supposed to work. The specific measurement we made was to take some of the soot and ask how much of the rare isotopes are stuck together in this way that I mentioned. The answer is the molecules from Hayabusa 2 are really clumpy. The rare isotopes really, really stick to each other in a way you would never see in a terrestrial environment. This is evidence that they formed in ices, in the interstellar medium. The chemistry of life, in a way, begins in the interstellar space. So I'm about to don't do it, I'm almost done. I really promise. I really promise. So what comes next? So the Hayabusa 2 mission, it's not over. It won't be over 10 years from now. It won't be over 20 years from now. We will be studying further molecules. There's tens of thousands of them. All of them tell a story. We want to figure out ways to study the solid materials, the organic matter. You and I are organic, but we're solids, I hope. Most organic matter is complex. How do we study it? What new materials will come from MMX? New technologies that must be developed to broaden our capacities to answer these questions. And finally, I'm a participant in the sample return across the solar system. KISS's contribution to this subject. How do we think broadly about the future of sample return science? That's all.
All right, thanks, John. How phenomenal to receive spontaneously a sample from asteroid by USPS or something, or FedEx maybe. Okay, last but not least, Chaz from JPL.
Yeah, hi, I'm Chaz Beichman. I work both at JPL and here on campus at the NASA Exoplanet Science Institute. And sort of from a personal standpoint, I just mentioned that I've had many years of connection to Japan. My sister lives in Japan. She's a professor of Japanese literature at a Japanese university. She writes books about Japanese poetry, no plays, shiki, basho, which will be known to our Japanese guests and maybe a few of the U.S. people who studied Japan at all. And I spent the summer in 1968 just hitchhiking all around both the main island and also up to Hokkaido, which I got to because I couldn't read the ferry schedule properly. And instead of going across to Aomori, I went all the way up to Hokkaido. But I got to see Hokkaido, so it was great. So my research background is in both infrared astronomy, with some of the missions listed at the top, the IRAS mission, Spitzer, ground-based telescopes, now JWST, and also shifting then over into exoplanet research, two missions that were terrific missions, the Terrestrial Planet Finder and the Space Interferometer mission, both of which were interferometers, which I'll come back to in a minute because it's a source of possible future collaboration with Japan. We didn't have Japan involved, therefore they were canceled. Well, they were canceled. Maybe they wouldn't have been if we'd had Japan involved. And also working on the Roman telescope, which again will have I'll highlight a Japanese involvement there, and also in the more distant future, something called the Habitable Worlds Observatory. So some of the past collaborations, past and present, our first scientific collaboration between our lab, the Infrared Processing Analysis Center, goes back to the early 90s, where ISAS had a mission called IRTS, the Infrared Telescope in Space. It was really Japan's first infrared mission, and we provided some of the data processing, in particular the pointing reconstruction. As I was talking earlier to some of our guests, I went to the Mitsubishi factory where they were actually developing the spacecraft to learn about the gyro system and all the things we would need to do the pointing reconstruction. More recently, there's a mission called the Nancy Roman Grace Telescope that's going up in a few years. There's a coronagraph that will be used to measure to separate the light of a planet from its host star using a very precise coronagraph. Japan is providing components into that. They're providing 100 nights of time on the Subaru telescope on Mauna Kea, and also for the microlensing part of Roman, there's a telescope in South Africa that's using NASA detectors on a Japanese instrument to do precursor work. Ground-based, there's an extensive history of collaboration between Japan and the US with the Subaru instrument. There's a Subaru infrared spectrometer instrument, and we're now developing a new instrument for the Keck telescope and eventually the 30-meter telescope with Motohiro Tamura at Todai. And you can see here that there's a small diffraction grating that Canon is developing for use in that instrument. It's a very high precision diffraction grating. And of course, we have a number of collaborations on JWST science proposals to be looking at exoplanet science in a number of different ways. Looking forward to the future, two of the collaborators that I've been working with most closely is Motohiro Tamura, who leads the Astrobiology Center. That's a very broad collaboration among Japanese research centers and universities. And we work with him on a number of projects. Also, Taro Matsuo, who's here in the audience, he came over yesterday and is leaving tonight just to be here at the meeting. And these are collaborations both on the ground and in space. We're looking at collaborations with a possible JAXA contribution to a future far infrared astronomy mission. We're looking at potential US contributions to a JAXA formation flying interferometry mission. So sort of harken back to what we had with the SIM interferometer and the terrestrial planet finder interferometer. We really need to develop ways to do high spatial resolution work either from the moon, as Gerard talked about, or in space, and they have different challenges, different advantages, and we look forward to working with the JAXA and ISAS personnel on that. And we're also looking for JAXA contributions to the Habitable Worlds Observatory, which eventually has the ambitious goal of finding life on an Earth outside our solar system. Thank you.
Thank you, Chas. Hitchhiking trip in Japan, 1968. That's phenomenal. Your next hitchhiking on Mars, maybe? All right, so as in the last panel, you can scan that QR code to ask questions to the panelists. And while you guys are typing in the questions, I will ask a few questions to each of you. So let's start with Stacy. I actually saw Hayabusa's return to Earth. I think I was, student somewhere. Phenomenal. So moving, a lot of drama. And I love to hear, because you spend a lot of time in Japan. I suppose you have a lot of episodes out of there. Would you like to share some of them?
Sure, yeah. Let's see. There's some I won't share, like the time we did karaoke. But it was wonderful. Our hosts and collaborators were amazing. Really took great care of us and were so wonderful. One thing that was funny though, this showed a lot about the culture and the effort that our hosts made to get to know us. This was back in the days of dial-up internet. So when you're overseas, you're in meetings all day, you don't get any news, and everything like that. And of course, you're jet lagged. It's a 12-hour time difference. So we walk in to the meeting, and none of us had really checked our email that morning. We're just too sleepy, and we walk in, and our guests say, "Oh, congratulations. We hear you have a new NASA Associate Administrator for Space Science." And we were like, oh my gosh, because Wes Huntress, if you remember, Wes Huntress had just stepped down, and we were all eager to know who would be the next person. And we were They're like, we didn't hear anything. Who was it? Who was it? I won't say the name, but it was someone, well, just shocking. I mean, it was just, what? That can't be right. Are you sure about that? And they're like, we believe the date is April 1st. Now, I mean, first of all, they're tracking what's going on at NASA well enough, right? And, they know that we're and they pulled the biggest prank on us, our own April Fools, and they turned it around on us. And I thought that was just so amazing, the attention that they're paying to what's going on in our lives and our calendar. So that was one of my funniest memories.
That's very funny. And Tomo, you were on the other side of Hayabusa and Hayabusa 2, right? Did you guys know each other at the time?
No. Okay, the Hayabusa era, I was in the United States.
Okay.
Can I read a bit of my story about the Hayabusa?
Please, I'd love to hear.
2010 is the time the Hayabusa spacecraft returned the sample, and then at that moment, I was the research researchers at the NASA's Johnson Space Center in Houston. So I didn't have any connection with the JAXA or scientists in Japan. But at that moment, I started my career in the United States as a scientist. I had some budget. I have collaborators. I have friends, and then I thought at that moment that I probably continue working in the United States. But 2010, I had a public viewing in NASA's Johnson Space Center, looking at the Hayabusa 2 re-entry to Earth. And around me, lots of those scientists in the United States, they are the scientists, so that they talk about the science of the Hayabusa mission. But I had a bit of emotional feeling that more than the science, and okay, this is my country's did a great job. And after that, I don't know why, but I started looking for a job in Japan. And then 2 years later, 2012, I got a position in Japan and back to Japan as the assistant professor in university. And now it's gone. So Hayabusa is not my science objective, but more than that, it's more emotional stuff. Yeah.
Great. And I also heard, Tomo, that you were responsible of transporting the samples from Japan to US, right? I got your phenomenal pictures.
I got a position in Japan. Yep. Okay. 6 years ago, I got a job in JAXA as a manager of the JAXA's curation facilities. And probably you almost forget about that. 2021 is during the COVID, and then the borders controls are very strict. But between the memorandum of understanding between the US and Japan, JAXA had to must transport sample from Japan to the United States. And then I am a manager, so the JAXA said, Tomo, you should go, you can go. And no one in the airport, no one in the airplane, except for me and cabin attendant. And, but the JAXA was kind of takes care of me and offer me a business class seat.
And offer the samples, the business class seat as well. Right?
Not because of me, but because of the sample. So I am one sheet for me, one for the sample. And also cabin attendants try to hide the suspicious, that's kind of a bomb-like box and up the blanket. And then after I landed in the Houston airport, and the airport security guards and also NASA's security staff approached me to the gate. No border controls. Everything is all the processes are clear. and then armed guys approached me to get into the NASA's band and then go to the Johnson Space Center. With any badges, I can directly go to the curations office. So I thought I was like a VIP. But after transfer the samples, and then NASA gave it to me the badge with the passport control, everything. So I thought that like I was not the VIP, but like a sample was a VIP. So yeah, this is my story. Yep.
And a part of this sample was mailed to John's lab.
Yeah. Not that sample, but like the other sample.
Okay.
Yeah.
So, John, a little bit of open-ended question, but how do those international collaborations help? How does it mean to advancing science in your area?
How does which?
How does the international collaborations?
This is a good question. So I think the most important thing is you set aside the organizations. Like, it's wonderful that JAXA exists. It's wonderful that NASA exists. God bless them, go on forever. But in the end, it's individuals working together, sharing their ideas, creative reactions to each other. Let me tell you a little bit about how I got into this community. It just, maybe it's fate or something, but I became interested in the study of the organic chemistry of extraterrestrial materials in Japan. It was the only time I've ever been there. I went to attend a conference in Yokohama. My wife was with me, and we went to Koyasan. If you know Koyasan, it was like probably the most magical 3 days of my life. But while I was at the conference, I had just invented a new technology for studying isotopic structures of things, and I was kind of fishing around for what area of science I wanted to explore with it, very open-minded. I was almost in a Zen state of just openness to ideas. And I wandered into a conference room where people were debating from all over the world, were debating. Maybe half of the people were scientists from Japan, half from Europe and North America. And they were debating what was known at the time about the origin and evolution of the organic chemistry that eventually leads to us, to life, if things go right. And I'm listening and listening and listening, the exchange of ideas, and I felt no one in this room knows how to say no to anything, okay? There's just lots of ideas are being shared and not parsed and honed and chopped away. How do we sharpen this? That was just my personal reaction to the people and what they were saying, and I wanted to respond. Who would have thought that these sorts of studies start with this negative thought? But I thought, I'll be the one who says no. I want to figure out, how do I observe things differently so I can disprove ideas and move this discussion forward? A very human experience, and so I went home and started working on media rights, and over 2 or 3 years develop enough credibility in my lab that people understand we can actually do this, and then I'm ready to revisit Japan in a way through colleagues. Now we're ready to figure out how to say yes to something. Can we prove something new? Can we learn something new? So I think we just have to spend time together. You have to be open to each other, spend time together, and out of that interaction comes the human instinct for new ideas. Yeah.
That's a great story for being open to new ideas, different views. Yeah. Related question to Charles, actually. So you have a lot of experiences, observations through your collaboration with European folks, right? And I suppose there might be different styles of working, different philosophies, cultures, and probably getting over the differences, how to collaborate smoothly. I wonder if you have any wisdom.
Yeah, absolutely. And John's story about everyone being so polite and nobody saying no is it actually sets the stage for an anecdote I shared with Hiro. This is back to the time when Stacy and I were starting to work with the Europeans on Mars sample return. At the time, NASA was doing a lot of work, early work with the Russian space agency. It was really kind of at the end of the Cold War, and they had a class that they taught on international relations, international project management. That was the official NASA offering. I joke it was like 18 hours of really, really good material crammed into a week-long class, a lot of it was not so useful, but there were some really good segments, and one of them was talking about those, how cultures relate to each other, and really getting that mindset that you shouldn't always think about, us versus them, or, we do things this way and they do things that way, that all of our cultures exist on a spectrum, that wherever we are, whoever we're working with, there will always be people to the left of us and people to the right of us, right? And even in things like being very polite versus being very direct, right? This is an example that often comes up in U.S. and Japan relations, but on the European perspective, you even see a gradient from north to south in Europe, right? If you're dealing with countries in Northern Europe, that for the U.S. is somewhere in the middle of that. The Northern European cultures come across to us as very brusque and very direct, and Southern European is a little bit more laid back, or how early do you have to show up for the meetings, or when are you late, depending on when the meeting starts, and I've known this for a number of years, but it was only in the last couple of months that the phrase was introduced to me that in Europe that's referred to as the distinction between potato Europe in the north and tomato Europe in the south. So it's just an important life lesson that when we are working across cultural boundaries, to always not always think of it as we do it this way and they do it that way. Wherever we are on that spectrum, there's somebody else even further to the left or further to the right than where we are. So.
Awesome. And I also would like to ask Chas, because you have like 3 or 4 decades of working together with Japan, right? I wonder how the US-Japan collaboration evolved over the decades, and how it's going to be going into the future.
I think one way that the Japanese effort has evolved, and I think it's partially due to our working together so closely, is certainly when I first started working on IRTS, it was clear that the ISAS effort started with some students and senior scientists thinking about the mission, designing the mission, building the mission, launching the mission, operating the mission, and then starting the cycle again without necessarily taking full advantage of the data that came from the mission. And one of the things that I think NASA has done that's really helped the overall space science community is putting enough resources in so that there's resource to let a broad community take advantage of the data from all that work. And I think there's now much more of a recognition of all the space astronomy efforts, that is the way you get the most impact for all the resources you've spent getting this fabulous machine up into space. RTS was relatively closed, but that then grew into the Akari mission that had a much bigger impact because there was a much greater involvement, this time with the European Space Agency, to make the data available and really let people relax a bit and use the science data that you spent so many years developing. And I see that very much going forward now in a way that I think has become the norm for these space astronomy missions. Is you're spending a lot of time and a lot of money getting these data. Let's take full advantage of it.
Awesome. Thank you, Chas. Let me pick up a few questions from the audience. Sorry, it's almost time. My assistant gonna start bugging me. Interestingly, there are a few questions about AI, probably because to go beyond, far away, the robot gonna be the first. So let me combine a few questions together. What do you think the impact of AI-enabled robot would be for future exploration deep into solar system? Does anybody want to take this question? Please.
The utilization of AI for missions that go further out into the solar system. Well, since I admitted to using AI for my graphics, I'll take a first swing. I mean, I do think what's intriguing is when we do these science missions, further and further out in the solar system, we've put a lot of effort into improving our communications, our ability to get data back from these missions. So we go to higher and higher frequencies over our curves. We go from S-band frequencies up to X-band to Ka, 30 gigahertz and so on, and now even to optical. But I think AI, machine learning, AI, data science on board, together with advanced computers and advanced processing, has the opportunity to do a lot more as we learn to trust it on board science, where the science instruments that go further out into the solar system, deep into the solar system, the outer planets, right, can take a whole lot of data and then have that synthesized and summarized on board and send back just the highlights, right, or at least send those back first. And then, based on what the AI or the machine learning on board algorithms have discovered, or where they shine a spotlight, then you can go back later and send back more data and more time. But I think there are opportunities there to have the missions take much more data than they could ever possibly send back, and let onboard AI sort of decide what the most interesting parts are.
Please.
Yeah, and you mentioned the once we learn to trust it, and that's a big step. But once we do learn to trust it, you could also think about bringing operations costs down by allowing the software to repair itself, diagnose a fault on board within a certain classification, whatever your risk tolerance is, and then go for it. That's a big, bold step.
Let me ask one last question. Sorry. Can deep space involve private ventures, or are the objectives mostly government? I know.
Who wants to touch that? I'll try.
Yeah, please.
I mean, that's an interesting question, especially in this time where, we have a new president, we have people that are from the public sector entering the government space, and I think the sky is probably the limit at this point. But yeah, first of all, for deep space missions, we have had commercial involvement from day one. I mean, our spacecraft, instruments, either, the components, we've always had that. The question is, I think, more along the lines of how much more involved, and could they run off and do a mission all by themselves? Well, I think that is the case. I mean, we're getting to the point where there very well could be what NASA has set up, at least in the past, has been an umbrella that says, okay, there are a few centers that we trust with a certain mission class to operate that mission, to manage and operate that mission. But oftentimes now, the spacecraft comes from a commercial vendor. So.
I might add, this is a question that motivates one of the newest big activities that's happening between the Caltech campus and JPL. It's called the Brinson Exploration Hub. And it basically asks the question, across all of the exploration space, the Earth's oceans, land, the sky, space, the outer solar system, the entire scope of exploration, how can you take a motivating concept and bring it to fruition in this new environment where there are many, many players with many different capabilities? How will you solve the problem of bringing them together for cost-effective, fast realization of your scientific goals? So I think, this is a great question.
Awesome. Okay, so I wish we have 3 more hours, but we have to stop here. Thank you so much. And together, we can boldly go where no robot has gone before. Thank you.